Thank you. Hey, I'm Toby Dewhurst. I'm an ocean engineer with Kelson Marine. And my pitch today is that if you want to make money growing seaweeds, you have to understand your cost drivers and how to improve them. At Kelson, we design farms all around the world. When I first got into seaweeds, my focus was on accuracy. It's easy to overpredict the loads on these structures by 200 or 300%, or underpredict the loads on the structures if you're using the wrong assumptions. So, under the auspices of RPE Mariner and working with great partners like Ocean Rainforest, we got to validate our tools against real full-scale measurements on farms in the ocean and calibrate our methodologies so that now we can have some confidence into these tools that we're building. After that, my focus was to build those methods into an efficient design framework so that we can answer questions like how well does the farm survive storms? And what's the tension distributions? Do the lines tangle? What's the distribution of flow speeds to the farm? As we've done that, what we found was that there are so many design trade-offs that can only be resolved by putting their impact into the overall cost of production. So what we've done over the past several years, working with the University of Maine, Woods Hole, UNH, is build a highly detailed techno-economic model based on real farm designs for every specific site that we're working with. And what this has allowed us to do is to build the coupled interactions into that techno-economic model that have been missing from previous techno-economic studies. I tried to map out the interactions that are in our model. It looks like this. That's the first 10%, so never mind. But maybe the most important part is that we've ground truth this against real financials from real operational farms. So to share some of the results from our findings here, I'll use my favorite case study, which is 16 kilometers off the coast of Maine in 100 meters of water depth with a specific exposure energy of about 7 joules per kilogram. And this is a challenging site that was chosen for potential co-location with floating offshore winds. Now, this metric of 7 joules per kilogram of specific exposure energy, that index is designed to synthesize the complex interactions of water depth, current speed, wave height, wave period into a single index that we can use for site selection and characterization. Now, in this past year, what we did is we tested the usefulness of that index by picking 32 different sites, real sites in the North Sea, and designing farms for each one of them, and evaluating how each one performed in 50-year storms and quantifying the required structural capacities as a function of that specific exposure energy. And we found that that's a much better predictor of the loads on the structure than some traditional methods like distance from shore, water depth, and significant wave height. Briefly, I mentioned 50-year storms, and we use this particular return period because that's what's specified in existing finfish standards. But seaweed, we're going to need our own design standards and guidelines at some point. Just one example. So we've started moving towards calculating these return probability contours, so you can look at what is the actual probability of various combinations of significant wave height, peak period, and current speed in this example. And you can see that some of the load cases that are specified for other aquaculture industries are actually well outside of that actual 50-year contour. And this, other industries can afford that kind of uncertainty. Seaweeds cannot. So we're going to need specific guidelines for our industry. But in the meantime, returning to this case study, let's look at a case study where we're doing annual harvest of Saccharina lutissima with an integrated nursery operation with a maximum allowable plot size of 40 acres, which is the legal limit for this particular site. So just two example results from this techno-economic study. The first is the actual impact of improving yield, whether through strain selection or other improvements. As you improve your yield, your revenue goes up, so do your costs. Which one goes up faster? Revenue goes up faster, but what we found is that there are diminishing returns on investment as you get to larger and larger yields, as you can continue to improve your overall yield on your farm. Now, Late last night, I actually took out the absolute values of the cost of production. They are in the manuscript, so, but these need to be considered in the full context of this particular case study. So I decided to make you read the paper for full appreciation of those. One more interesting finding from this particular case study. We get asked a lot, how large of a scale is necessary to achieve economic viability? In this particular case, and it's going to be different with every case, we get really good improvements, good economies of scale as you get up to about 120 hectares. After that, we see actually very little increased economy of scale with today's technologies, unless we have significant transformative improvements in mechanization and automation. So, to summarize, for years, we've been showing sensitivity studies, techno-economic sensitivity studies that look like this. And this is from our own publication 2 years ago, that says all that matters is yield and nothing else. But once we've actually integrated these complex interactions, increased costs that come with increased yield, vessel costs, fuel, labor costs that vary with distance from shore, etc., the actual sensitivity to some of the top cost drivers look like this. Yield is no longer king. It matters, but it's not the most important thing. So what we need to do is we need to really optimize our vessel expenditures. We need to really be really careful with fuel and maintenance costs for vessels and figure out how to drive those costs down at very large scales. We need to optimize our structural capex. Seaweed has one of the highest ratios of structural capex to actual biomass of all the aquaculture industries. We need to drive those down. And we need to drive down our harvest expenditures while maintaining yield, so that together we can successfully build an economically sustainable industry. Thanks. Thank you. Hey, I'm Toby Dewhurst. I'm an ocean engineer with